Hey there, today we're talking Newton's first law of motion. Now, of Newton's famous three laws, the first two work to explain the relationship between force and motion, more specifically, changes in motion or acceleration. Now, the first law explains the qualitative relationship, and then the second law expands on that a little bit with quantitative or numbers to better explain that relationship. Today, we're looking at the qualitative end of things. Now, before we get started, if you're taking notes, I would recommend writing anything that's blue. If it's orange, it's optional. If you want to write it down, then feel free. And anything that's white or gray, you can just read. All right, so to do a little bit of a recap with forces, we know balanced forces mean that everything cancels out, leaving us with zero leftover force, so zero net force. And we won't see an object accelerate with balanced forces acting on it. If forces are unbalanced, meaning there's some leftover force after everything cancels out, we are going to see some acceleration in that object because net force is not zero. And remember, objects act as if there's only one force acting on them at any given time, and that force is whatever net force is acting on that object. All right, so we're just going to jump right into it. I'm just going to give it to you. Newton's first law of motion. Objects at rest stay at rest unless acted upon by an unbalanced force, and objects in motion stay in motion at the same speed in the same direction unless acted upon by an unbalanced force. I like to interpret that as matter is lazy. It doesn't want to change. If it's sitting there at rest, it wants to stay at rest. If it's in motion, it wants to keep moving at the same speed in the same direction without changing. If you want to get matter to change, you gotta force it. Now, I could keep talking all day about this stuff, but it might be easier to show you. It's sometimes a little easier to visualize if you actually have visuals. I'm going to use the PhET simulation here to demonstrate Newton's first law of motion in a few parts. I'm going to turn off friction for now, and I'll explain why I did that later. First, an object at rest will stay at rest unless acted upon by an unbalanced force. Now, if forces are unbalanced, there is some leftover force in some direction, and that is what we call the net force. Remember, objects will act as if there's only that one force, the net force, acting on it. Now, in this case, there is no net force. The sum of all the forces equals zero right now, so net force is zero. And so there's no reason for this thing to be moving. It's just going to sit there. If I unbalance forces by applying more force to one side, the object will now accelerate. And so in this case, we have a sum of forces of 50 newtons to the right. We now have some acceleration, and so we see this thing start to speed up in this case. Next, an object will stay in motion at the same speed and direction unless acted upon by an unbalanced force. So this object is now moving. Net force right now is zero. All the forces on it sum to zero, meaning the forces are balanced. So this object will behave as if no force is acting on it. It will continue to move at this speed in this direction forever. And why wouldn't it? There's nothing making it change that, so it will continue to move this way forever. If I unbalance forces to one side, notice that the motion changes. It now accelerates. I can accelerate it in the direction of motion or in the direction against motion, but either way it's going to accelerate. And this is due to the fact that I unbalanced forces on it. Now, I think I know what you're thinking. You're thinking, okay, this is a simulation. In real life, things always stop when you slide them. I could slide a book across a table, it's gonna stop. And you're right, in real life it does. But in real life, the rules have not changed. There's a very good reason for that, and it is still due to unbalanced forces. Check it out. In a real-world example, things don't typically continue sliding like this forever. But in the real world, there's something that is missing in this simulation. Remember earlier when I turned off friction? If we turn friction back on, notice what happens. Forces are immediately unbalanced, and this object accelerates. Friction always works against the direction of motion, and so friction is always going to slow things down. Our sum of forces is in the direction opposite of motion, and we see this accelerating to a stop. This is typically what we're used to in the real world. So for most things, when I slide them across a surface, a table, it's going to slide to a stop. If I slide this textbook across a table, it's going to stop. But if I could somehow turn off friction, then once I release the object, once I'm no longer applying a force, forces should go balanced and it will act as if there is no force acting on it. Its motion remains unchanged. It will not accelerate. Now I can kind of do that. I can kind of remove friction with one of these toy air pucks here. And what this does is spins a fan and it puts a cushion of air under this puck so that when it's on the ground, it floats above the ground, removing almost all friction. This air puck will remain at rest until I apply a force to it. When I kick it, it accelerates. There is very little friction acting on this air puck, so once I stop applying a force, the forces on this air puck are relatively balanced. This means that the air puck will act as if no forces are acting on it. This is why it keeps moving. There is no force to change its motion, so why would it change? If I don't turn the fan on, then forces will be unbalanced due to friction, and the object will slide to a stop as expected. Now this applies to all matter. All matter is lazy, whether it be you, me, bowling ball, feather, brick, whatever. All matter wants to resist accelerating. Now, does all matter resist accelerating the same? In other words, do we need to apply the same amount of force to get anything to accelerate in the same way? Think about that for a second. If I want to accelerate a toy car and a real car, do I use the same force? I'm ready. I'm heading for the parking lot. No, of course not. That would be ridiculous. And if you answered no, then you are correct. Different things require different amounts of force. Check this out. In this example, I have two smart carts. The blue cart has 1 kilogram of added mass. The red cart is unchanged. I'm going to accelerate them at the same rate by pushing on them with a ruler. The graph on the screen shows us the force applied to both carts to accelerate them. Notice that I have to apply more force to accelerate the more massive blue cart at the same rate as the red cart. So yes, different objects do resist acceleration differently, and there is actually a name for this resistance to changes in motion, this resistance to acceleration, this property of matter.
Inertia is a property of matter.
Yep, you hear it every time you watch Bill Nye. Inertia is a property of matter. So the property of matter that describes that resistance to acceleration, inertia. More inertia means more difficult to accelerate, so more difficult to speed up, more difficult to slow down, more difficult to turn. It takes more force to do that. Less inertia, much easier. So why do some things have more inertia and some things have less inertia? What causes something to have more inertia? Let's look at a couple examples. Look at the pairs of objects and try to figure out which one you think resists acceleration more. Which one would be harder to accelerate? Which one would need more force between those two objects in those groups? Between a toy car and a real car, which one is harder to accelerate? The real car, so it has more inertia. Between 1 brick and 10 bricks, which one is harder to accelerate? The 10 bricks. 10 bricks has more inertia. Between a ton of bricks and a ton of feathers, which is harder to accelerate? Well, it turns out a ton of bricks and a ton of feathers both have the same inertia. They both are equally as difficult to accelerate. So with that said, based on everything we've seen, what do you think determines an object's inertia? Well, you'd be correct if you said mass. An object's mass can be used to measure its inertia. In the cart demo, the blue cart had more mass and therefore more inertia. This is why it took more force to accelerate it at the same rate as the red cart. And it's very important to remember that we can indicate inertia with mass and not weight. Now, weight works on Earth because, well, if something has a lot of mass, it has a lot of weight. Weight and mass are proportional to each other, and we'll get into that with gravity later. But out in space, especially deep space where you're not near a gravitational source, something with a lot of mass has zero weight. That doesn't mean that it would be really easy to accelerate. If, say, some big space rock was heading for the planet and you thought, well, hey, out in space things are weightless, I got this, and you go up there and you try to get yourself in front of it, well, it still has quite a bit of mass, meaning it has a lot of inertia, and we know things with a lot of inertia take a lot of force to accelerate. So moral of the story is, don't stick yourself in front of a large space rock. So just to reiterate, because it is so important, we use mass to indicate inertia, not weight, because mass is constant anywhere, weight is dependent on gravity. So to summarize, the more massive something is, the more inertia it has, and the more it's going to resist acceleration. So more mass, it's going to be harder to accelerate. And that makes sense when you really think about it from a real-world perspective. If something's more massive and typically on Earth heavier, it's going to be harder to push. Now, since Newton's first law is describing this resistance to acceleration that all mass shares, and resistance to acceleration is referred to as inertia, we can call this law Newton's law of inertia. Makes sense, right? All right, a little pop quiz here for you. Here's a few examples for you to see if you can identify which has more inertia Now, there is another misconception that I want to talk about, and that's between inertia and force. They are not the same thing. Inertia is not force. Force is not inertia. Force is simply a push or a pull. Inertia is describing a resistance to acceleration, and it requires force to overcome that resistance. So force and inertia are not the same. Write that down. So before we wrap up, I want to leave you with a little thought experiment. This is something you can actually try if you're ever in a moving car as the passenger. Don't ever try this as the driver, please. But when you're sitting in the passenger seat or in the back seat or wherever, take a ball or something small and just toss it upwards while still within the car. Where will it land and why? Try to use the concept of inertia to explain what happens. Alrighty, I hope this helped. If you have any further questions, please make sure you talk to your teacher. Thanks for watching. Have a good one.